You might remember that the Barker 11 chipping code is going to be used in order to convey information in a DSSS 802.11 configuration, right? So it's going to take 11 2 megahertz channels, combine them all together, send out each bit. But how does it actually send that out? I mean, we're not sending electrical current that either is there or not there. I mean, it's a particular waveform that needs to be detected. Here's what happens. Using something called differential binary phase shift keying, essentially the wireless signal, the wavelength, can be adjusted. It can be flipped at any point in time as it is exiting the antenna. When the antenna sends out a signal in which the wavelength is flipped, we're sending out a 1. You see right there how, and this line right there, that the signal was coming down, it comes back up, but then it comes back down again. That is indicative of the fact that we are using that this next bit is a 1. You see right here where we've got the signal coming down and up, and then, just keeps on going up and down and up and down. Nothing seems to have changed. It did not go through a phase shift. Oh, that's because this wave represents a 0. Every time we flip, it's a 1. Every time we don't flip, it's a 0. So here we were coming down and we flipped. So therefore, it's a 1. So it doesn't matter whether it's at the bottom or the top. Anytime we change our phase shift, that's indicating a 1. So that allows, with 11 channels, each sending out information, 1 megabits per second. All right, that's our speed. That's our throughput. Somebody came up with a way to make this even better, though, and that's called our differential quadrature phase shift keying. Same idea, only it says instead of flipping it, let's rotate it 90 degrees, or 0 degrees, 90 degrees, 180 degrees, or 270 degrees. And we'll have binary values, 0, 0, 0, 1, 1, 1, or 1, 0, represented by each of those different phase shifts. So, gang, something to recognize here is what we're seeing here. Let me take a chunk. Here's a chunk that represents a 0. That same distance, that same waveform now can represent 2 bits instead of 1. See, that same wavelength that was received over a period of time used to be able to say it's a 0, but now it can say it's a 0 and another 0. See how it's got 2 bits that it's representing because it didn't change phase at all? It's doubled the amount of information it can send without having to, within the same waveform. So because of that, it doubles the throughput to 2 megabits per second. But it gets even better, because in DSSS, we also have something called complementary key coding. Complementary key coding says, all right, we're going to move beyond the coding, the chipping code with that 1 to 11 ratio. Instead, we're going to go to a 4 bits per symbol, 6-bit chipping code. So we've got a 4 to 6 ratio, 4 bits per symbol, 6-bit chipping code with a 2-bit buffer. What that means is we end up sending out a byte of information, right? 8 bits. First 2 bits are used to indicate the orientation of what we're sending out. And then here's our waveform. And again, just notice that, so for example, here might be 90, here's 0, here's 180, here's 270, right? So we're seeing those different quadrature angles that we were looking at before. But now what we're able to do is represent entire codes. We're representing patterns based upon the orientation. In other words, if we go left, up, down, right, that's a 4-bit code, that can represent something greater than itself. That could actually represent a value of, because you are dealing with not just the orientations, but the orientations in sequence, it means more than the sum of its parts. So that value could indicate, instead of just being 0, let's say 0, 1, 1, 1, something like that. Yes, it could represent that, and that would give it 16 possible values. But when we look at these in terms of their relationship to each other, these in that order represent a larger value. Okay, so by doing this, I've reduced the amount of chipping code that I'm using, right? Instead of 1 to 11, now we've got this 4 to 6 ratio. And in fact, I could even double it because what I can do is take the leading bits that are used in here as well as the chipping bits themselves, and I can actually go to an 8 to 8 ratio. For every 8 bits that are used, 8 bits are being sent. I'm not really chipping anymore. I'm using this polyphase complementary code. I'm using a coding mechanism to reference it, and the orientation bits and everything else are used to describe the content. So when we move to this model, we go to 5.5 megabits per second. If we move to the more advanced model that uses all the bits, we move to 11 megabits per second. But what have I lost? Remember all that redundancy, that 11 to 1 redundancy we had using the DBPSK when we were using binary phase shift keying? Everything was just a 1 or a 0 with 11 channels that were sending that out across. Man, that's a lot of redundancy. So what happens is, as we have an access point and we have a client that is next to that access point, when they are, what we find is that when they are close, put it this way here, if my device is close to the access point, I'm going to stick with that 11 megabits per second model. Move it farther away, it's going to be, ooh, things are a little riskier. I better put some chipping code back in there, but we'll use our more efficient chipping code. Let's go with CCK and that 4 to 6 ratio. What if I get farther out? Whoa, things are really risky. I better drop down to DQPSK, where I'm using the Quadrature phase shift keying, but I'm just tracking everything 2 bits at a time, 2 megabits per second. Get even farther out. Whoa, I don't even trust myself to read 90-degree phase shifts. Let's just flip it. 0 or 180. I'm down to binary phase shift keying. I'm down to 1 megabit per second. What happens when I then get real close again? Oh, hey, now we can go back to our best speeds. So speeds adjust because we're putting more information into that same space. Less redundancy, more information being compacted into that information across DSS. That's why we see that distance change our bandwidth. It's not attenuation when we're just randomly losing things. It's we might lose things, so therefore we drop back to a model that can still intelligently, correctly move that data across even with a high degree of data loss.